This video is about a probably soon to be real or released product by Lee Hart, who I've done quite a few videos on various of his retro computer project kits. And this one is not a computer kit, but it is a retro electronics kit and has some relation to retro computers because it's about a binary watch, meaning that the display is in binary instead of in decimal. Now, decimal watches and decimal clocks are hardly new. There have been many commercial products that are timekeepers that have decimal or binary displays, and there are even wristwatches one can buy today which are commercial products and use tiny microcontrollers, surface mount parts, and so on to achieve the result. But this is probably the only one that is watch size, fully functional, and uses only parts that date from the 1970s, the dawn of retro computing. Of course, it wasn't retro, it was nowtro back then. But, you know, things like the Altair 8800 and the IMSI 8080 and other computers of that ilk, which used all binary displays in their native form. So Lee sent me a kit of the prototype, or at least pre-production version of this binary watch, and this video is about that. And presumably the production version of it that'll be available, I believe it's targeted for the 2025 Vintage Computer Festival Midwest for its initial availability. Okay, we have the double-sided and quite thin, wafer-thin printed circuit board. We have one green LED, 10 red LEDs, a Zener diode, 3 1N4148s, that's the same as a 1N914 diodes, just regular low-power silicon diodes, 5 resistors, transistor, battery holder and battery, 2 tactile push buttons, an assortment of small capacitors. And that's it. It's hard to believe that tiny little capacitor is 4.7, 4.8 microfarads, but it is. And although it's shown as having a polarity on the schematic, the pins are the same length and there are no markings on the part saying which side would be positive, so I'm guessing it's not. Okay, here's the assembly process, starting with the circuit board, just a good view of the front of it, and then a view of the rear of it. The first components to go on the board are the 3 ICs. These are all CMOS parts. 2 of them are 16 pins, and the third one is 14 pins. One of them is oriented one way and the other 2 are oriented in the opposite direction. That's an area that a builder could get tripped on if they're not paying attention. And because of parts that'll get mounted on the back of the board, such as the battery holder, it's necessary to clip all the pins close to the board after soldering. Up next are the 10 red LEDs. They fit in very tightly between the ICs, no extra space there. And you kind of have to put them in, hold them tight to the board, solder one leg, and then while pressing them hard against the board and straight and level, reheat that and then solder the other pin and repeat that for the others. The resistors are next. 5 of them stand on end to take up less board space, with the 6th one laying flat in the normal orientation. These are all 1/8 watt resistors, so they're quite tiny. And then the capacitors are mounted. They all go in at weird angles because they fit around the periphery of the board for the most part, and of course the board is curved. And then the handful of diodes go in, and these are oriented so their cathodes point down towards the board, and their anode ends, the leads, go up and bend over and go back. So they all end up standing on their nose, so to speak, or standing on their cathodes. And it is important to install the diodes correctly in this regard, because there's a couple of places where the pads are so close, if you put the cathode ends in those holes, then the two diodes that'll be adjacent to each other are actually trying to take up some of the same space. So it's important to orient them correctly. There's a tiny little cylindrical crystal, and that's showing up on the left of the top LED in this view, a little silver can laying flat on the board. And then the two tactile switches solder on. And again, the battery holder gets mounted behind these, so you want to make sure all of this is done right, and that you inspect all the solder joints very carefully through a magnifying lens if you have it, because you are going to have a hard time repairing any damage here or even seeing it once the battery holder is mounted. Now that all the parts are on the front of the board, there's the two parts on the back, the green LED and the battery holder. I chose to mount the green LED on its side and kind of pointing towards the center of the board because I wanted it to have the least height, but as it turns out, the battery holder, when the battery's in it, is about the same height as the LED, so I needn't to have done it this way. I could have just had it standing up flat against the board in its normal orientation. And here's the battery holder mounted. I had to kind of twist the LED a little bit to make sure it cleared the holder, and that's another reason to not do it the way I did it here. This LED isn't really for normal viewing. It's after all on the back side of the watch, but it serves an electronic purpose primarily. It's being used as a Zener diode, and a secondary function that it's some kind of an indication of how much charge is left in the battery. As you can see, the green LED gets dimmer and finally goes out when the battery voltage is insufficient. And then the included battery gets snapped into its holder. This is a standard type. It's a CR2032. The CMOS circuitry uses essentially no power except when logic states are changing, which is, for the most part, very slow on something like this, except for the clock circuit. The LED display is not working except when you push the display button, so it's not taking battery power. So the battery should last a fairly long time. Maybe not as long as coin cell batteries in modern digital watches, but still a reasonably long amount of time. With the battery installed and the display button being pushed with my left fingertip in this photo, the LED display lights up on the front. In this case, it's just a random count, and it happens to be one that only has one LED turned on, but it's not a real count until you set the thing. Okay, here's after I've set the watch. It's currently set to 4:06. 4:06 is the time. The top four LEDs show the hour, so it's in a binary 4 here. And the bottom 6 LEDs show the minutes. And since it's those two on, that's a 4 plus a 2, so it's 6. Alright, I'm going to wake up the display. The current time is about 4:04. There's no AM or PM on this. So I hit the button, and it reads 4 and 4. So that's correct. Because the first one is 1, that's 2, and that's 4. 1, 2, and 4. Now it went to 5, so it's keeping time at least. It's advancing on its own. And that's what my watch says, 4:05. I'm going to hold the display button down now and see if I can see it transition. I let off the button. Oop, there it just transitioned. Okay, 4:06. So it's keeping up more or less with the time. Alright, I'm going to go through the circuit, describe how this works. First, just another overview. So this is a design by Lee Hart. I've got a number of videos showing various products and kits that he makes, that he's designed and makes. This one is one that's being prepared. It's not commercially available at the time of making this video, but it's the retro binary watch, and it's sort of a retro nerdy device. It allows people who are savvy with binary to wear a timekeeping device that presents its minutes and hours in binary rather than the usual decimal. It consists of an oscillator and clock, a set of binary dividers, some reset logic for groups of dividers, and that's necessary to provide a rollover. For example, when you get to 59 minutes, that it'll roll over to 0 minutes, things like that. And 2 banks of LEDs to depict the minutes and hours in binary format. It's powered from a single 3-volt coin battery like a CR2032 type, and there's no power switch. Whenever the battery's in, it runs just like any other digital watch. It uses only parts that were available in the 1970s, all vintage electronic components, in other words, and it uses all through-hole construction. It's a very tight circuit. You couldn't really pack any more components into it. But now to get into the circuit theory, because, you know, you would look at this and say, how can I get a whole clock that's running off of 3 CMOS chips? They're not microprocessors, microcontrollers, they're not dedicated clock ICs, they're just simple logic ICs. How do you get a clock that keeps time and depicts hours and minutes in binary with just such a small amount of circuitry? Well, the clock's divided into several sections. First off, there's the oscillator, and that's down here. It's a classic crystal oscillator circuit. Of course, you need to have some sort of an inversion in there. You can't just have the crystal and its support capacitors and resistors. You need to have something that inverts. It could be a transistor, it could be inverter in a logic gate package. In this case, is stealing some internal logic from a CMOS 4521 IC, which is a divider IC, and it just happens to have some auxiliary components in it that can be used, and it's has what's called an input 1 and an output 1, input 2 and output 2. They're separate circuits internally, and they're not directly involved with the rest of the function of the chip, but they can be pressed into service to do that. And in this instance, it's just using an inverter that happens to be in the logic between the input 2 and the output 2. So that's serving as the inverter necessary for the crystal oscillator to work. And then the second bit of auxiliary circuitry is just being used, to condition the input coming in on input 1, and it's borrowing the FET and a series internal resistance of about 1K in service of the power supply circuit for the LEDs. So that again doesn't have anything to do with the rest of the function of the chip. Now the oscillator is running at 32.768 kilohertz, and you need to divide that down. So just like with a frequency counter or something else, you divide down a higher frequency through lots of stages of division, and by doing so you continually reduce the error in the crystal oscillator. So even small deviations in the crystal frequency, by the time you do all that division, end up being pretty much insignificant errors. So the bulk of this IC is doing a lot of dividing down of that oscillator, and then it finally presents several outputs. They're all called, you know, Q18, 19, 20, and so on. Q18 is the first one that's brought out as an external signal, and that, after all the division, produces a 1 hertz clock. And then when you divide it by 2 again, it becomes a 1 second clock on Q19, or Q16 rather, which isn't being used here. Q17 is another one that's internal. And so again, these are Q18 through 24, and the Qs I'm describing are internal points that are not brought out of the IC. By the time you get up to Q18, the first one, that's a 4-second pulse, or 4-second clock. The next one's an 8-second clock, the next one's 16 seconds, then 32, then 64. Q23 is a 128-second clock, and we're still using that. And then Q24 is the last one, that's 256 seconds, and we are not using that signal. The only ones we're using are the Q20, which is the 16-second clock, the 32-second clock, the 64-second, and the 128-second. Those 4 signals. The two signals here, the Q22 and the Q23, are used to directly drive 2 LEDs in the display. The Q22, as I said before, is a 64-second clock signal, and that's treated as a 1-minute clock. And then the Q23 is 128 seconds, and that's being treated as a 2-minute clock. So these 2 LEDs, I'll deal with where the signals return after they go through the LEDs, but that's how the least significant 2 bits of the minutes display are operated from this IC directly. Now I want to go inside what's happening on this part of this IC, so I broke it out with a sketch. We have this display push button. It's got a pull-up resistor to VDD. That's being used instead of VCC here, but it's a 3-volt power supply coming from the 3-volt battery. There's no conditioning or anything. It's just directly off the plus side of the battery, and circuit ground is directly off the minus side of the battery. So when you're not pushing the button, the resistor pulls this point up, logic high, and then there's a capacitor across the switch. It's shown up here, but it's in parallel with the switch, so it's like this in my sketch. The display button, the pull-up resistor, the capacitor across it. This is a fairly high value, as is this, and the RC time constant of this, assuming CMOS logic levels, this whole circuit is CMOS, works out to be about a 4-second delay. So if you even ignore the fact the switch is there, it's like a power-up reset circuit. So when you first turn the watch on, that capacitor briefly acts like a short and pulls this signal low, pulling it down against that pull-up resistor. And after that takes about 4 seconds for it to charge up enough that it looks like a logic high signal again. But if you push the button here, it shorts out the capacitor, and then even after you release the button, until it takes 4 seconds to charge back up, it holds the logic level here low. So whether it's on power up or when you push the display button, this goes low for 4 seconds. If you hold the button in longer, then it'll be even longer than 4 seconds. Internally to the IC, between its input pin, input 1 that is, and output 1, is a circuit that looks essentially like this. I simplified it a little bit, but this is essentially what's there. There's the input 1 signal, there's the reset signal to the IC, and that's shown over here, coming from up around there. Those two are combined in an AND function, but the inputs are inverted, and then it has an inversion on the output too, so it's like a NAND with inverted inputs. If you actually map out what this logic IC is doing, and these two signals here, I'm calling them A and B just for this chart, before the inversions on the inputs, if you just had the usual binary pattern, and then you take into account the inversions here, and then solve it as a AND function, and then invert the output, this is the truth table you get. What does that look like? That looks like the truth table for an OR function. So you can actually think of this thing as an OR gate without any inversions. Reset is active high, so when you pull this high, again, if you think about this as an OR, when you pull this high, it goes through and you get a 1 out here. At the same time, if you don't push the display button, this is a logical high, and treating this as an OR, you'd have a logic high out here. Only when you're not pushing the display button, and this is logic 0, and also you're not doing a reset, so this is logic 0, then if you think of this as an OR function, a 0 and a 0 on the input of an OR gives you a 0 output. It's a logic low, in other words. And that'll come in useful when we talk about the power supply for the LEDs. So anyway, that's an example of the logic that's kind of being borrowed from this IC and is not directly involved in the counting, although the signal might be used internally in some way, but it's not a primary function. Now, I mentioned that we're also stealing some internal circuitry from here to make the oscillator work. So in between pins 6 and 4 over here, input 1 and output 1, you just really have an inverter. I didn't pencil that in, I'll put it in right now. An inverter. And then you've got a classic circuit for a 1 inverter crystal oscillator. 2 resistors, 2 capacitors, a crystal, and the inverter. And it's going to oscillate at the crystal frequency of 32.768 kilohertz. And that's the signal that you'll get out of it. And that will be the clock that goes into the entire bank of divide by 2 logic blocks that are inside this, which whittle it down to the aforementioned signals that have various durations in minutes and so on. Now we're going to have all these LEDs that are operating at various times. None of them will be on, most of them will be on, various combinations will be on, and also the battery voltage can change. It's nominally 3 volts, but as you use the watch, it gradually will draw the battery voltage down, so it's nice to have an indication that the battery's getting low and maybe the circuit isn't working quite right because the voltage is marginal. And you'd also like to hold the voltage here constant, which helps keep the LED brightness at a nice, even, and consistent level. So I'm going to talk about that circuit now. This one caused me to scratch my head. I had some emails back and forth with Lee Hart while I was puzzling over it and finally got it figured out. So I'm going to describe what I figured out with Lee's gentle prodding to make me think about it a little differently than I was initially. So let's just look over simple voltage regulators and not actually voltage regulators, because a true voltage regulator samples the output and uses a feedback circuit to adjust the output constantly to make sure it stays at the desired voltage, regardless of changes in load and power supply voltage and other things. But a simpler circuit that's often used as a power supply isn't truly regulated, but it's still something of a voltage reference with power delivering capability. The simplest version of that is kind of like this. This is a transistor used basically as a switch. And I'm using an NPN transistor here. It seems like people just inherently visualize how these work a little better. If you had a V plus here, you know, whatever your raw power supply voltage is, you connect it to an NPN transistor's collector, and you connect the load to the emitter, and you don't want to have unrestricted base current going, so you put a resistor here from the raw supply to the base, so you get some current going this way. It goes into the base, out the emitter, so you've got some base to emitter current, and then the transistor does its thing and amplifies that current by the gain of the transistor, and you get that much current going from the collector to the emitter. And if there's a particular load resistance out here, then that current develops a voltage across the load, and that's what voltage you have out here. Now, if you do nothing different than this and change the load a lot, then the load current or the load resistance or both, then you're going to have some voltage change out here. And this type of circuit, again, is primarily a switch. It's not even a voltage reference. But what if you wanted to turn it into a voltage reference? Well, we follow the arrow. All we do is we take a Zener diode and tie it from the base to ground. So we have the same thing, but now some of the current is going this way and some of the current is going this way, and that depends on the voltage of the Zener diode. You can look at it another way. Even though a transistor is really a current-operated device, not a voltage-operated device like an FET is, you can think of it in a simplistic sort of way as saying, well, let's say this is 1.8 volt Zener. So there's going to be 1.8 volts from here to ground, and if I subtract the 0.6 volt base to emitter voltage drop from that, you might end up with something like 1.2 volts out here. That's assuming, no load to speak of, or no load variance anyway. So then you've established some voltage that's lower than V+, and it's following the voltage of this, but again, it's not regulated, so it can still, if you have a significant change in the load out here, it's still not going to be exactly the voltage that's tied to the Zener, but it's a way to get some kind of a voltage reference out of this circuit without adding hardly any extra complexity. You see this kind of thing a lot in circuits where older circuits, because now voltage regulators are dirt cheap, but back when they weren't, or IC voltage regulators weren't even available, this was a very common circuit. If you knew what your load was and it wasn't going to change very much, this worked just fine. Almost like a voltage regulator under those conditions. Well, what if you didn't have a Zener diode? Or you didn't have a Zener diode of the right voltage to get the desired output? Well, another way you could do it is by having multiple regular diodes forward biased. We know that a typical diode that's forward biased has some current going through it, will have a voltage drop across it. Now that voltage drop isn't a constant. It can change somewhat with the amount of current, but let's say you had this resistor set up in such a way that you'd have a certain known current going here, and that would establish a certain known voltage drop. And let's say that it's 0.6 volts per diode, so it adds up to 1.8 volt. In that case, this transistor doesn't know the difference between this 1.8 volt Zener and this stack of regular diodes. And you could use a Zener and a diode, or you can do all sorts of things to get exactly the voltage you want to get here. But so that's just another version of this circuit. Now, what if you didn't want to do it this way, but you still wanted the same voltage? Another way to do it is to, I mentioned you could have a combination of diodes and Zeners in here. What if you did this? You have a Zener diode, but it's a forward biased Zener diode instead of a reverse biased Zener like this, in which case it acts pretty much like a regular diode that's forward biased. But being a Zener, its voltage may not be exactly what the forward voltage of a regular diode is. You'd have to look in the spec sheet. Let's just say it's 0.7 volts in this example. And then we put a LED in here, forward biased. An LED that's forward biased kind of acts like a Zener diode pointing in the other direction. It has its own kind of Zener voltage. Well, a typical LED is going to have more than this, but let's just say this happens to have 1.1 volt voltage drop across it. You add that up to the 0.7 volt and you've got your 1.8 volts like we had in these other examples. So this circuit would do essentially the same thing as these other two circuits. So now we've evolved that circuit till we have this. We've got an NPN transistor, we've got a resistor, we've got a Zener diode, we've got a forward biased LED. And we still have the same voltage out here. Again, not really regulated, but it has some consistency to it. But this circuit that we're dealing with has a PNP transistor. If you're trying to convert an NPN transistor circuit to PNP, you pretty much have to reverse everything. We take this circuit and we drop a PNP transistor into it instead. It's not going to be sourcing current anymore, it's going to be sinking current in the direction of the arrow. Instead of the positive end of the power supply, it's going to be the other end of the power supply, in other words, ground. So we put ground out here. The ground that was here becomes the positive of the power supply, and we flop the diodes facing the other direction. So now, instead of facing away from the transistor to ground, they're going away from the power supply to the transistor. But it's the same two devices. It's going to work exactly the same way, except now instead of sourcing current into the load, it's sinking current from the load. Of course, the other side of the load is connected to V+, where in this case the other side of the load would have been connected to ground. So that gets flopped upside down too. So your raw voltage would go through the load, come into here, the current would be sunk, and it would return to ground. And the combination of the voltage drop here and the current through here and the current through here results in base emitter current here, which causes this transistor to conduct a certain amount, which controls the current through it. And because the load has a certain resistance, Ohm's law tells us what the voltage will be out there. So it's really the same thing, just it's a PNP version of the NPN circuit. Well, now let's just redraw that a little bit. Instead of this awkward thing where I come down and then hook around for V+, I'm just going to flip this circuit upside down. So now V+ is up here, and you've got the Zener that's forward biased, and the LED, but it's the same thing. And we go into the base of the transistor, but now I'm drawing the transistor off to the side, still the base of the transistor. The collector is still going to ground. The emitter is going to the V out, just like this is, where current is coming into the circuit. And then instead of having this resistor here from the base to a ground potential, I get it this way. I come out of this point in the circuit, I go into the IC, I go through its internal output resistance and through the FET that's in there to ground. Well, when that FET is turned on, it's like this point being ground, so this end of the resistor is essentially tied to ground, just like it was up here. And we've completed the translation. Now I can go over here and recognize this as this as this, and this here we know is what's inside this IC at that pin. So whenever we want to have the LEDs out here be powered, we have to allow current to come out of them and go to ground, so this transistor has to be turned on. And that means we have to be able to be sinking current to ground, so this point here has to be operated by the rest of the circuitry in the IC, so this point is pulling towards ground. And just like was in this sketch. And that's exactly what this IC does whenever I push the display button or this capacitor is charging up after a power on. Now, while this circuit is working, there is current flowing through here, and that LED therefore has current going through it in a forward direction, and the LED is going to make some light. As long as there's enough voltage out here, then that's what's going to happen. But as the battery voltage gets less and less, as it wears down, the amount of current going through here diminishes till the LED can't function anymore and it stops lighting. So in that sense, if the LED, this green LED, is glowing merrily, then we know that this circuit is pulling adequate current out of the LEDs over here to make them light decently. But when the battery voltage gets too low, then eventually this LED will shut off, and that's an indication that it's time to change the battery. So you get not only voltage regulation of a sort, at least voltage ballpark for the LEDs so they maintain a reasonably constant brightness, but you also have an indication of battery health. And you get all of that from this circuit here. You may have noticed that when I was going through these Q outputs of this IC, I mentioned that the way it divides down, because it's going in a binary pattern starting with 1 second, it goes from 1 second to 2 to 4 to 8 to 16 to 32 to 64, which we're using to drive the 1 minute LED, but 64 seconds is not 1 minute, and 128 seconds is not 2 minutes. So there's more to it than just that. And what we have up here is a reset. I mentioned before that this big counter divider IC has a reset to it, which resets all the internal counters back to all zeros, so it has to start again from 0. It's been counting up the pulses from this oscillator and dividing them down and then counting. But look at this, we have Q20, 21, 22, and 23 all brought together up here into a 4-input AND gate. And then the output of that comes back and operates the reset. So let's look at this AND gate we have with the 4 inputs. And as I mentioned just a second ago, it's the 16 second, the 32 second, the 64 second, and the 128 second outputs of the divider. So while the individual bits are sort of odd values when you compare it to what a clock or a watch would want, when you add them up, add their binary values up, we add 16 plus 32 plus 64 plus 128, that's assuming all of those bits are turned on, that comes to a nice 240 seconds. If you divide that by 60, so we can see how many minutes it is, 240 does divide down into a nice even 4 minutes. So with these odd binary values, or binary weights, this particular combination does add up to 240 seconds. So when the count reaches 240 seconds, not 256 seconds, which would be the next binary weight, when it just reaches 240 seconds, then all these bits are on, that wraps back around and resets this back to all zeros. Therefore, this last LED, it doesn't stay on quite as long, and the end result is that this point here toggles at the 4-minute mark. It's the most significant bit we're using, and starting from 0 when you've reset this and counting up until all 4 of these bits are turned on, that is 4 minutes. As soon as 4 minutes happens, then all these bits are on, you do the reset, it goes back to 0 and starts again. Therefore, every time we reach a state of all 4 on, then this point goes away, and then it takes 4 minutes before, well, not 4 minutes, but it takes some time before this comes on again. Therefore, you have a regular pulse here. So let's look at that a different way. This bit comes on at some point in time during the count up to 240 seconds. It comes on considerably before it gets to 240 seconds. It comes on at the 128 second mark. But at the end of the 4-minute period, then this goes away because the reset has happened and everything's been turned back to 0, including this bit. So this bit here goes from high to low once every 4 minutes. It's a high to low transition, and it couples through this capacitor. And in conjunction with this resistor that's pulling high, this point here briefly goes low and then goes high again. That's the nature of an RC circuit like this on a signal that's doing a transition like we're talking about here. So you capture that high to low transition, and that makes a brief pulse. The length of that pulse is determined by the resistor and the capacitor, and that pulse is applied to the input of this next IC. Well, this IC is the rest of the circuit that counts up in minutes. We already have the 1-minute and the 2-minute LEDs coming off of some outputs of this counter, and now we have to get the rest of them, and we have to be able to count up to 60 minutes before you roll over to the next hour. And it takes 6 bits to count up that high. So we have to get these other 4 bits after these 2 are already established, and this guy does it. Every 4 minutes we get that pulse like I just talked about, and that is the clock that causes the counters in this IC to count up, and they go through the binary pattern of their outputs, only 4 outputs this time. One of them gives me the 4-minute LED, one gives me the 8-minute LED, one's the 16-minute, and one's the 32-minute LED, going up in those binary weights. 4, 8, 16, 32, each one twice the last one. Well, we want to reset as soon as we hit this count of 60. Now, on a regular clock, you don't see 60 on the face of a clock, and your digital watch doesn't go to 60 seconds. It goes up to 59 seconds and rolls back to 0. But to do that, you have to get to 60 first and then just immediately turn it back to 0 so fast you can't tell it happens, and that's what happens here. Once we get to a point where all of these 4 bits are on, and if you add that up, it adds up to 60 minutes. So this little combination of things here, this resistor and these diodes, are acting as a sort of a AND gate. It's essentially doing what this did, but there's only so many ICs on this tiny little circuit board, and there isn't room for another 4-input AND gate. So it's done built out of this. And by the way, this doesn't count all the way up to the full binary weighted value. As I was stumbling on trying to say earlier, if we were going all the way up to a 32 weight binary, that would include the 1 weighted bit and the 2 weighted bit before getting to the 4, the 8, the 16, and the 32. So if you added all those 6 bits up, it would be higher. It would be 64 by the time they're all turned on, or, I mean, there's 64 combinations, to put it that way, right? But here we only have 4 bits we're looking at. And 32 plus 16 plus 8 plus 4 is 60, not 64. And that's because we're not including the 2-minute and the 1-minute bit in this AND gate. So once we get to the point in this binary pattern where the 32-minute LED is turned on, and then these guys have to count up in binary again, it's trying to, because it's high here, it's trying to pull the reset here high and thereby reset this back to 0. But it can't, because some combination, 1 or more of these 3 bits, is still going to be 0 at some point in time as they're counting up. So as long as one of them is 0, that'll pull this point back low through the diode or diodes, and only when all 4 or all 3 of these are on, then there's no way for these diodes to pull it low. And finally, this one being high does pull the reset high, and this goes back to 0. So it does count up to 60 on here, but in the blink of an eye, it resets back to 0. So while it was technically on 60 for a very brief time, it happens so fast before it goes away you wouldn't even know it. So we can pretend it's just going from 0 to 59 instead of from 1 to 60. And that's how we accomplish the minutes display. Now visually, of course, we still take into account the part of the number that's down here. Something I forgot to mention before, this part of the IC has a clock input and an enable input. There's really a gate inside of here, and you can clock this with either the clock input or the enable input or some combination of both of them. If you look at the data sheet for this IC, you can kind of program what kind of input it's looking for to clock the counter. And that can be a positive going signal, it can be a negative going signal, or a low going signal. In the case where you take the clock input and tie it to ground, then the enable input is looking for a negative or low going transition, and that's what it uses. Not the whole signal, just the transition. That's when it increments the counter in here. So this chip has been programmed to look only for that high to low transition as a place where it does the counting to the next increment. Now the other half of that same IC is over here, and this is the one that controls the hours. So every time the counters over here are reset, this acts like a low going transition into this counter's enable. It's the same thing. Its clock is tied to ground, so it's looking for a high to low transition on this enable input, and it's monitoring the highest bit here. So just like over here, this bit turns on, but then the other ones have to count up to reach the full binary value, and then this goes away. So once every 60 minutes, this signal transitions from high to low, and that high to low goes through this resistor and goes directly to the enable of this counter, thereby making it increment, and it increments up through a binary pattern, and the most significant bit, like the most significant bit here had the highest minutes value, the most significant bit in this counter has the highest hours value. We're calling it the 8 hour, and the other ones are the 4, the 2, the 1 hour LEDs. So in this case, we don't have to use diodes and a resistor to make an AND gate. Instead, we have the other half of the IC that had this 4-input AND gate. So we've got this one available, and it's monitoring not all of the bits, only 3 of the bits. But one of them is operating 2 inputs to the gate, so it's really a 3-input AND gate the way it's being used here. It's monitoring the 1 hour, and it's monitoring the 4 hour, and it's monitoring the 8 hour bits. It's not bothering with the 2 hour bit. So that particular pattern where the 8 hours on, the 4 hours on, and the 1 hour is on, which is what we get in order to satisfy this AND, that adds up to 13. Well, we know we don't have a watch that says 13 hours, but it does have 12 hours. So when it gets to the point where these 2 LEDs are on, that's reading 12 hours. 8 plus 4 is 12. And then finally, when it clocks up to the point of the 1 hour guy coming on, in addition to those, that adds up to 13. As soon as that combination is there, this AND gate reacts, wraps around, and it resets this guy back to 0. So even though it technically gets to 13, you'll never see it because it is reset so quickly. So it seems to go from 0 up to 12, but you don't have 0 hours. You have 0 minutes, 0 through 59, but with hours, you don't have 0 hours. You've got 1 through 12. So this counter resets to 0, but you can't let it sit on 0 because that's another state that we have to get off of so fast that nobody will notice it happened. So as soon as this reset occurs and the counter resets, then the reset goes away because the condition it's looking for out here has gone away. So you have a transition here that is going from high when reset is on to low when reset has turned back off. So that's a high to low transition. And that wraps back around through this capacitor and tickles the enable input again. So as soon as it's reset, it immediately gets another pulse on the enable input, which causes it to count 1 time. So it immediately gets off of the count of 0 and goes to the count of 1, just in a blink of an eye. So that's the way this counter is cleverly set up to count hours from 1 to 12 and display only those binary patterns. So some things that are a little awkward about this circuit. As the circuit is currently designed, there's no way to set the minutes in the lowest resolution. You can't directly set the 1 minute and the 2 minute LEDs. They're just whatever they are. Now if you're really coordinated and plan ahead and do it just right, you can get the time set on the rest of the minutes and the hours so it's almost where you want it to be, and then stop doing the setting, wait for the low minutes to catch up, and then make the final set, and then at that point everything is synchronized with the real time and you can just let it run. That would be one way of doing it. Lee Hart has been talking about some sort of a hack which could be put on here to include these extra 2 LEDs in the set, but it didn't seem like there's a good way of doing it without adding too many components and making it impossible to fit it all on such a small circuit board. I've made a couple of suggestions on ways I would possibly approach it, and it wouldn't be a way to actually set them, but it would be a way to freeze them so that at least they're not counting. So for example, you could wait till the real time, the real time of day per some accurate clock has all zeros for minutes, and freeze this guy ahead of time when it's on that pattern with the 1 and the 2 being 0, and then freeze it so it can't change from that. Wait until the real time comes by when it's all zeros, and just before that, well, with this still being frozen, use the set button to crank this guy up so all the rest of the minutes are also 0 and the hours whatever you want it to be, and then finally take it out of freeze right when the real time reaches that spot. So you're synchronizing this to the real time. That would be another way of doing it, but at this point in time none of those have been implemented, so it's a little awkward to get it set and frustrating to get it set to exactly the right time. It can be off by a few minutes, which frankly my cheap Timex watch is usually off by 2 or 3 minutes, and usually it's not a problem. So for something like this, I'm not too excited about that. Now I had already talked about how the display button worked, but I don't think I talked about how the set button worked. It's another situation where there's a switch going to ground and then a pull-up resistor. It has the same thing here. And what it does is every time you push the button, this gets pulled down to ground, and when you release the button, it goes back up. So it transitions from high to low. And we know that the enable input to this counter increments on a high to low transition. So every time you push the button, it increments this one. When you release the button, nothing happens. It only reacts to button pushes, not button releases. So there aren't that many choices here. You can't set these, and you've only got 4 LEDs for the rest of the minutes. So that's not that many combinations. So relatively few button pushes can get you through an entire hour of counting 4 bits of minutes. And then you can do that pretty quickly, just a bunch of tap, 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 taps on the set button. And then that rolls over to hours, and there's only 12 hours, so it's not like it's an incredibly large number of times you may have to push the button to go through all the possible time values. What really sucks is if you miss it up and have to do it again, but that's the way it has to be set. You just have to keep pushing the button until you increment through the patterns until you get the pattern the way you want it to be for hours and minutes. And then maybe or maybe not you get the last least significant minutes to line up with reality. So there's a small hack. My board is the pre-production, so prototype stage of the design. And Lee Hart has told me he's already designed the revision B circuit board, which is pretty much the same. The main difference being that a diode has been added, and I penciled it in on my schematic here. It goes from the push button resistor node for the display button through the diode to the button resistor button node for the set button. So this way, without the diode, in order to set it, in order to see what you're setting, you have to hold the display button down so the LEDs are visible, and then tap away at the set button. By putting this diode in, every time you push the set button, it pulls the display bit low through the diode. But the diode blocks it working the other way, so pushing the display button by itself does not change the setting. So that's a logical change, and because every time you short this point to ground, either by the button here or through the button via this diode, this capacitor gets discharged and it has to charge back up, which takes about 4 seconds. So unless you're tapping very slowly with this, as soon as you start using the set button to change the time on the watch, the display is basically on constantly, and only when you stop pushing the set button for a few seconds would the display shut off again. So that's a good improvement, and apparently on the Rev B version of the board, the holes, pads, and circuit board foils are there in the design, so you don't have to kludge it. On mine, I had to tack it on to the back of the circuit board, and it's a tricky proposition, but I managed to get it done. It'll be much nicer on the Rev B boards. So here's a final photo showing the kludged in diode bodge. The diode and its leads are encapsulated here in a piece of small shrink tubing, and it just reaches around the battery holder and solders on to one switch at one end of the board and the other switch at the other end of the board. I don't expect anybody who gets one of these kits going forward will have to deal with such a bodge, however. It's just something that the pre-production guys like me have to mess with.